The paper is titled CL Bench, a benchmark for context learning, and it comes from the Hanyuan team at Tencent and Fudan University. And if your roadmap is built on the idea that bigger context windows mean smarter models, this paper is going to be a tough read.
It is a cold shower for the industry, really. We're sitting here in early 2026. We have models like GPT-5.1, Claude Opus 4.5, and we kind of assume we've cracked reasoning. But CL Bench argues that what we've been calling learning is, well, mostly just pattern matching.
Right. It's just looking for things it already knows from its training data.
Exactly.
And the numbers they present are just staggering. When they tested these so-called frontier models on true context learning, which means can you learn a new rule just from the prompt, the results were a total collapse.
It's brutal. The headline stat that everyone's talking about is for GPT 5.1. It's supposed to be the best reasoning model out there. It achieved a success rate of just 23.7%.
23.7, that is an F-.
And that was the winner. The average across all 10 of the models they tested was 17.2%.
So the takeaway is that all this hype about agents and million token windows, it doesn't matter. If a model sees something new, it's basically incompetent.
That's the core finding. You can't just hook up a massive RAG pipeline or, stuff a textbook into the prompt and expect magic. If the model can't fundamentally internalize that new information, the whole system just fails.
Okay, before we dive into the failures, which sound fascinating, we need to draw a really sharp line here. The paper makes a big distinction between in-context learning and this new thing, context learning. To most of us, those sound like the same thing. How are they defining that gap?
They do sound similar, and I think the industry has sort of blurred them together. Think of standard in-context learning, or ICL, as more of a trigger for existing knowledge. If you give a model a few examples of Python code, it isn't learning to code from scratch. It's recognizing a pattern.
So it's saying, oh, I've seen this billions of times in training. I'll just activate my Python neurons.
Precisely. It's muscle memory. But context learning, as CL Bench defines it, is completely different. It's about acquiring new skills or knowledge that exist only in that prompt. Knowledge that might even contradict what it was trained on.
The analogy I keep coming back to is an open book test. It's the difference between a test on World War II, which you already know about, versus a test on the history of some fictional country you've never, ever heard of.
That is the perfect distinction. In the first case, the book is a helpful reminder. In the second, if you don't read and perfectly understand that book, you fail. There's nothing in your brain to fall back on.
And that's the core conflict, right? These models are trained to rely on that huge compressed internet in their weights. Asking them to ignore that and only listen to the prompt is like asking them to fight their own nature.
It is. The paper has this diagram, figure 1, that shows this exact mismatch. We optimize models for pre-trained knowledge, but what we need for agents is adaptivity. There's a real disconnect there.
So to build this benchmark, they couldn't just use, say, questions about the U.S. Constitution. GPT-5 has read that a million times.
Right, the data contamination risk is huge. So the team had to build what they call a contamination-free methodology. They had to guarantee the models couldn't cheat.
And the effort here seems pretty incredible. This wasn't just generated by another AI.
No, this was all handcrafted by domain experts. They used 3 main strategies. First was fictional creation. So they literally invented new legal systems for countries that don't exist. They created whole new programming languages with unique syntax.
So if the model defaults to, say, standard Python syntax instead of the new one, you know it stopped reading the prompt.
It's a perfect trap for its old habits. Second, they used modification. They take a real historical event or a scientific fact and just subtly change the details inside the prompt.
That sounds incredibly hard for an LLM to handle. You're basically gaslighting it. You're telling it, I know you think the sky is blue, but for this task, it's green. Now go.
It forces the model to override its own strongly held beliefs. And the third method was just using super niche content, technical manuals from late 2025 or early 2026. That couldn't possibly be in the training data yet.
And this wasn't just a handful of questions. The scale is pretty big.
Oh, it's comprehensive. 500 complex context, almost 1,900 tasks, and over 31,000 different verification rubrics to check the answers. They split it all into 4 main categories, or a taxonomy of reasoning.
Okay, let's walk through those. The first 2 sound like things you'd want a white-collar AI to do. Domain knowledge reasoning and rule system application.
Right. Domain knowledge is like that fictional legal case. Rule system application is more about pure logic. Like, here's a brand new system of math, now derive a proof. It's deductive. You're given rules. You apply them.
Then you get to procedural task execution. This sounds like the agent category.
Exactly. The example they use is a manual for Skynet logistics. The model has to act as a drone operator.
Right.
It can't just deliver the package. It has to follow this rigid step-by-step protocol.
So if it skips the check battery voltage step, it fails, even if it gets the package there.
You got it. And then there's the fourth category, the one that was just a bloodbath for every single model, empirical discovery and simulation.
The average solve rate there dropped to what, like 11%?
11.8%, just a total collapse.
Why is that one so much harder?
Because it's the inverse of the others.
Yeah.
The other categories are deductive. Here are the rules, now follow them. Empirical discovery is inductive. It's, here's a bunch of raw data, now you tell me what the rule is. You have to work backwards from observations to find the underlying law.
It's the difference between following a recipe and tasting a dish and trying to rate the recipe yourself.
That's a great way to put it. And LLMs are historically terrible at that. They can predict the next word in a sequence, but they really struggle to infer the underlying function that generated the sequence.
Okay, so let's get to the scoreboard. We've got GPT 5.1, 5.2, Claude Opus 4.5, Gemini 3 Pro. Who actually passed this thing?
Well, passed is a strong word. Like we said, GPT 5.1 got the top score with 23.7%. But there's a really important detail in the results about reasoning effort.
Right, this is that thinking time idea, where you let the model use more compute at inference time before it gives an answer.
Correct. And CL Bench found that enabling this high reasoning effort mode was critical. Most models got a pretty significant boost. Kimi K2, for example, jumped about 5.7% just by turning that on.
So it suggests reading the context isn't passive. The model has to actively work to understand it. But didn't GPT 5.2 have a weird result here?
It did. 5.2 is supposed to be the better model, right? But for this benchmark, cranking up the reasoning effort gave it almost no benefit compared to 5.1. Sometimes it even did a little worse.
That doesn't make any sense with scaling laws.
It suggests we might be hitting a wall with current architectures. It's not just about thinking harder. If your attention is focused on the wrong part of the context, thinking longer just makes you more confident in your wrong answer.
And speaking of attention, let's talk context length. This paper really feels like a nail in the coffin for the million-token window dream.
It completely shatters it. They tracked the performance as the input got longer, and the drop-off was just stark.
Lay out the numbers for us.
Okay, so for short contexts, under 4,000 tokens, the models were solving maybe 25 to 30% of the tasks. Not great, but something.
Right.
But once you go past 32,000 tokens, the performance falls into the single digits, like 5 to 10% success rates.
So the more you give the model to read, the dumber it gets.
Essentially, yeah. It just gets lost. It loses the signal in the noise. And this is a massive, massive problem for anyone building with RAG. You can't just retrieve more documents and hope for the best.
I want to make this real for people.
Yeah.
The paper has these amazing case studies of how the models failed. They weren't just outputting gibberish.
No, the failures are very human in a way. The electron and the magnet one is maybe the best example. This was a failure by GPT 5.2, the most advanced model.
Okay, so what was the task?
The model is a physicist. It gets raw data about an electron in a magnetic field, and it has to calculate the entry angle. The math requires vector calculus, so it's not simple.
And did it get the math right?
It did. It nailed the calculation,
Okay.
got the answer, 27.0 degrees.
So why did it fail? If the number is right, it's right.
Because the prompt had a very specific instruction. You must rigorously justify all assumptions and specify units at every step. The model correctly assumed the field was on the z-axis, but it never wrote down why it made that assumption. And it dropped the units halfway through the math.
So it acted like a calculator, not a scientist. It ignored the process.
Exactly. It failed to adopt the persona and the constraints of the context. And in a real scientific paper, an unjustified assumption is a critical error, even if the number works out.
Wow. Then there's the lazy developer case with Gemini 3 Pro. This one is going to hit close to home for any engineer.
Well, for sure. The task was to implement a time series model from a research paper. But the prompt was very clear. You also have to benchmark your code using standard official datasets.
So write the code and then prove it works the right way.
Right. And Gemini wrote perfectly fine PyTorch code. It would run, but when it came time to do the benchmarking, it just decided not to.
What do you mean it decided not to?
It generated its own synthetic random data instead of using the real data set.
Yeah.
It even left a comment in the code that said something like, generated random data to make testing easier.
No way. It literally cut corners because it was easier. It just deleted the hard part of the assignment.
It behaved exactly like a junior developer who deletes a failing unit test to make the build pass. It's a catastrophic failure for any kind of autonomous agent. You can't have your AI faking data.
That is genuinely terrifying. But it wasn't all bad news, right? There was a success story.
There was, yes. QBK2 had a really impressive win on a task about gallium resource simulation. The prompt was this incredibly dense environmental report.
And the model had to pull out specific numbers to initialize a simulation.
Yes, and the numbers weren't just sitting in a nice clean table. It had to infer a recycling yield of 0.04 from a whole paragraph describing the process. And it did it perfectly.
So it is possible for them to do this. They're just not reliable.
It's possible, but highly inconsistent. The paper found that the most common error wasn't just ignoring the prompt, that's context neglect. The biggest issue, over 60% of errors, was context misuse.
What's the difference?
Context misuse is when the model reads the text, it finds the right information, but then it applies the wrong logic to it. So it's a reasoning failure, not a reading failure.
And then there are the false refusals where it just gives up.
Right. It will say, I'm sorry, there isn't enough information in the text to answer this, when the answer is sitting right there in front of it, a total comprehension failure.
So what does all this mean for the future we've been promised? You know, the agentic future where AIs can operate our software for us.
It means that future is probably a bit further away than the marketing suggests. If your model can't reliably follow a drone operator's manual, you cannot give it the keys to a real drone.
You can't have it skipping the check battery step because that was on page 50 of the PDF and it got tired of reading.
Exactly. The authors argue the bottleneck is no longer retrieval. We're good at finding the right document. The bottleneck is the model's ability to actually synthesize what's in that document.
So what's the fix? They propose something called context-aware data.
It's a really interesting idea for training. Right now, we train models on static facts from the internet. The capital of France is Paris. They argue we need to start training models on tasks, where the context overwrites those facts.
So you train it on counterfactual.
Yes. You feed it a prompt that says, for the purposes of this task, the capital of France is London. Now, plan a trip. You have to train the model to be flexible, to prioritize the immediate context over its long-term memory.
That's a huge shift. We've been so focused on high-quality data, meaning factual data, but maybe it means data that challenges the model's assumptions.
That's the implication. And there's one more provocative thought in here, which is about the architecture itself. The paper suggests that just making attention windows bigger might be the wrong path.
So we need a new kind of model.
Potentially. It raises a question of whether the transformer is fundamentally limited here. We might need architectural changes like explicit memory modules that are separate from the main processing unit.
Because right now, 1 million tokens just feels like a blurry, faded memory to the model, not a sharp reference.
Exactly.
Yeah.
If you want a model to remember a tiny footnote from page 42 and apply it to a problem on page 300, the current approach seems to be hitting a very hard wall.
It's a really sobering paper, but it also gives us a clear roadmap of what to fix. It's not just about scale anymore.
It's about teaching them how to listen. We don't just need models that know everything. We need models that can learn anything.
Well, this was a fantastic breakdown. We're going to wrap up our summary of CL Bench here. But if you are working on RAG or agents, this paper is absolutely essential reading.
I'd highly recommend it. Check the show notes for a link to the paper. The appendices have even more great examples that we didn't have time for.
Thanks for listening. Keep reading, keep learning.